Well, good morning. We're starting chapter 4 in our text, and we're talking about current sources. And the picture right here is a picture of a good current source. That is a way of showing a current source with that arrow, and that's our symbol for a current source, and that's what we're going to use from now on out with regard to current sources. So basically, that gives you an idea how current sources look as we are looking at right now, how to put a current source together. So with that in mind, we're going to start looking at applications of current sources. So this is a kind of a guarantee. No matter where we're at on that resistor, we can go on one side to 0 ohms, and we can go to the other side to 10k ohms, and no matter where we're at on that resistor, it's going to guarantee 3 milliamps through that circuit. So that's a different way of looking at things, but it's saying we're going to guarantee the current instead of we're going to guarantee the voltage. So that's a different look, but that's exactly what that arrow does. Okay, and they can either be dependent or independent, and we're going to give you an example later on of a dependent current source. But we're going to ask the question, if you really want to know that, how do you do a current source, really most of the time inside of, when you look inside the black box, it's a voltage source and some kind of an R Thevenin. But that said, you have to ask the situation how you're going to deal with this. So if you have a resistor out here that you're going to hang out here between the A and B terminals, you can then say, okay, what would be the resistance in here so that this would act like a current source, so there would be almost a constant current no matter what the value of the resistance is out here. So that's what we're going to be asking. So basically it's this: if this is 100 times smaller than this resistor, then you can say this acts like a current source. And I'm going to show you the example here. In this example, with the wiper at the bottom, excuse me, with the wiper at the top, you get 0 resistance. So in that case, R Thevenin is the 100 meg, 10 times 10 to the 6th, and the voltage is 1,000 volts. So that gives you 1,000, or gives you 100 microamps. Now at the bottom, the resistor gives you the RL, which would be 100k plus the 10 meg, which basically gives you 99 microamps. And you look at the 100 and you look at the 99 and say, across the range of this resistor, I'm almost a constant current, and that's why we can say we've got a constant current source. This is a constant current source if this resistor is a lot smaller than this resistor, and that's how you can make an equivalency of them. Okay, so that gives you an idea of the how you can make a current source, constant current source, with using a voltage supply. Okay. So there is also the idea of a dependent or an independent. So this would be an independent current source. No matter what this circuit is doing, this circuit over here is going to pump out 2 milliamps. Over here, it's a dependent source with whatever this I over here is. This is going to be a multiplication of that. And you say, well, where does this ever happen in the real world? This is an example of a transistor circuit, and that's exactly how a transistor works. A bipolar junction transistor, that's exactly how it works. We're not going to worry too much about this in this course, but that's what a dependent current source looks like. It's 100 times the value of I. Right there's the value of I. And here's your value of I right here. Okay, so how this changes makes this change over here. How would you ever use something like this? This is an amplifier, isn't it? This is a small circuit. This is a big circuit, so this is going to pump up a lot more current than this circuit over here does. So we're amplifying current. Okay, so we now come up with this idea of a current source and a voltage equivalent. So Thevenin is our voltage, simplest circuit for voltage. Norton is its equivalent, and we're going to try to look at that and see exactly how things look. Okay, so here we have a circuit that pumps 1 milliamp around this circuit. So it pumps 1 milliamp and it goes through the 3K, so our voltage from A to B is 3 volts. So now, how do we get the Thevenin equivalent circuit? Well, you know, for a voltage source, you just jumper it out, right? For a current source, you open it up. So you basically take open terminals. So you basically do the exact opposite. So our resistance here would be 3K. Only this counts. This one does not count at all. Okay, so that gives you an idea of how to supply a Thevenin equivalent circuit to a circuit. Now, here is a circuit that says, okay, no matter what, I want to find V Thevenin. So V Thevenin here is 5 milliamps, steams around through there, and that gives me or 5 milliamps, or 5 volts, excuse me, across the AB terminals with this AB terminals removed. So in this case, you got 5 volts, 5 volts, and you come back here and you look at this and you say, okay, I'm going to come down through here. I cannot come through here because it's open circuited, but I can come through here, which is 1K. So I have 3K plus 1K, or 4K. So there's your 4K and your 5 volts. That's our Thevenin equivalent circuit to everything to the left of the AB terminal. So I can find my Thevenin equivalent circuit of a circuit with a current source in it. Now, the following example uses superposition to find the Thevenin equivalent circuit. So this one is a little different. So here I have voltage and I have current, and I want to find, how do you do superposition? So with superposition, what did you do? You shorted the other supply, didn't you? In this case, you open the current supply, you short the voltage supply. So basically, when I do this with current, or with voltage, I remove it. Do you see that? I remove the supply. So here is the current supply. This is my starting circuit. I remove it. I take it out. It's no longer there. So when I solve for voltage, the current supply is gone. When I solve for voltage, the voltage supply, when I solve for current, the voltage supply is not gone, it's shorted. Did everybody see that? So when you take this one out, you open it up and you cut it out and you don't use it. When you take this one out, you short across it. So basically, I want to find the voltage across the AB terminals with a current supply and a voltage supply. So this one is pretty easy. It's what? It's 4 volts, and here I have, excuse me, it's 5 volts. It's 4 over 4 plus 4, or 5. Here I have a combination of a 4K and a 4K, which is 2K. So I have my 2 milliamps going through a 2K, that's 4 volts. So I have 5 volts and 4 volts is 9 volts. And then I look at my my R Thevenin, and I started here. I started A, and I walk down, and here's 4K. It's in parallel with 4K. This is gone, so I've got a 2K output. So I have 9 volts and 2 volts. And 2K, so that's 9 volts and 2K is my Thevenin equivalent circuit of this whole thing. So that's how you solve a Thevenin equivalent circuit of a circuit with both voltage supplies and current supplies in. You open these up and you short these when they're not used. Now, the Norton circuit is what? It's like Thevenin, but it uses the current supply instead of the voltage supply. And what's inside of a Norton is I shorted load in parallel with R Thevenin. Okay, so this is what would be inside if you were using current. This would be the current equivalent of the voltage divider, or of the voltage Thevenin. So what would be V Thevenin? I shorted load times R Thevenin. So basically, all you do is you get the current of the I shorted load and you put the R Thevenin in parallel with the I shorted load, and this gives me the current equivalent of the original circuit, or the Thevenin circuit. So basically, that's how you convert from V Thevenin to R Thevenin. So you need to know this basic equation. I shorted load is V Thevenin over R Thevenin, and then you can convert from one to the other. So here I'm going to say find the Norton equivalent of this circuit. So I start with 12 volts, and I basically ask the question, what would be the voltage across and the resistance? Or I could say find I shorted load. So I take out the 2K, and I add a short here. So basically, if I short this out, what would be my I shorted load? Well, it's 12 volts divided by 6K, or 2 milliamps. So there's my 2 milliamps. Then I ask the question, if you short this voltage out, I have 6K in parallel with 3K, or 2K. So basically, this is my Norton equivalent of this circuit. Okay? Another way of finding it would be find V Thevenin, and then find R Thevenin, and then find I shorted load by using the equation V Thevenin over R Thevenin, and find I shorted load that way. But this is equivalent to this. Then you add your 2K back in, and away you go. So there's a number of ways of finding I shorted load, and one of them is to short out the output. One of the other ways is just to find V Thevenin and R Thevenin, and then find the I shorted load from those two. So how would I convert from Thevenin to Norton? Well, it's V Thevenin over R Thevenin is I shorted load. Take the 2K and move it down here. So one way is to short the output and find it that way. One way just to look at it and say V over R is I, and that's 2 milliamps. And then take this R over here and move it down here, and you're done. It's fairly simple. It really is. It just kind of, these are a bunch of strange rules. I understand that, but this is how you do it. So the Norton is the complement of the Thevenin. Since we usually have voltage, it is referred to as Thevenin, and Thevenin is preferred over Norton. Sometimes current is the lead, however, and Norton may be used instead of Thevenin, but both work. Both of these work. Okay. Now, how do we find a circuit that is a Norton circuit? Well, convert the Norton circuit to a Thevenin and find that either will produce the same result. All right, so if I have Norton, I can convert it to Thevenin. If I have Thevenin, I convert it to Norton. Either way works. Okay, so I have 3 milliamps and 5K, 15 volts. Move the 5K over, and I've got my Thevenin. Here, I've got a circuit that basically says, I've got current, I've got 5 volts. How do I find the current through here? Well, if you cut it right there and say, I want to convert this to Thevenin, because this looks like Norton to me, and it is Norton, multiply the 5 times the 3, so 15 volts, move the 5K up here. Now I can find the current through this. It's much easier, in my opinion, than finding this, but it's either way works. But this way is, in my opinion, a little bit easier. So you can use the Thevenin equivalent to find your voltage, or find your current. Okay, now, all that aside, we'll practice those a little bit. We're not going to practice them a lot, because Norton is not as important as Thevenin. If you can do the Thevenin, pretty much that's where we want to get to. But if you can do Thevenin, we will maybe from time to time toss in a Norton, but not as much. So now we want to talk about the power formula. The power formula is what? It's V times I. And that's how you figure power. Okay? It's also joules per second, but we don't worry about that formula. We just basically worry about P equals V times I. Okay, so let that soak in. P equals V times I. And the units are watts. Okay, now there's alternate ways of doing it. It's I squared R or V squared over R, but these are based on the fact that V equals IR. So you can find it either of any of these three ways. But V times I will get you there. Okay? V times I is the way to go. Okay, so I also have what we call matched load power. And this is a way of determining how do I get the most bang for my buck. In other words, how do I get the most out of a circuit? And let's say you have a speaker system. How do you get the most out of those speakers? How do you get the most power out of those speakers? Well, the way to do that is to match the Thevenin equivalent circuit of your speaker system to the ohms of the speaker. And many times it says match to 3 ohms or whatever, 8 ohms or whatever. But you have to match the ohms here to the ohms here, and that gives you the most bang for your buck, or the most power out. So the matched load gives me my best output of my circuit, and that's why this is important. Okay. So how do you find out the maximum the maximum power out of this circuit right here? Well, you set the RL to the same as the Thevenin current. So how do I find the maximum power out? Set RL equal to R Thevenin. Now what does that do? That drops your voltage across here from 12 volts to 6 volts. So you only get 6 volts out. But that said, you're going to get more power out if you do that. Now you say, well, what if I vary the R in here? Could that have an effect? Yes, it could. But most of the times you're stuck with the black box. You're stuck with this part up here. You have to match this power to this part, because this is your given. This is what you can vary. And the way to get the most out of it is to match this to this. Okay? In other words, you can get the most power out if I take this R to 0 and put this to whatever value you want. You get your most power out. You agree with that? But that isn't your option. You don't have the option of changing this. You do have an option of changing this. So that's what we're talking about, the matched load power. Okay? So there's some questions at the end of this chapter that actually show you that that's where you get your peak output power, V times I, is when you do match the RL to the R Thevenin. Okay, applications. So it is more important to match the output resistance when the signal is weak as in a TV antenna, and that's very important. This is a good example of the need to match the antenna resistance closely. Okay, so if we don't have, obviously at R equals 0, this is the best way to go, but we usually don't have that as an option. We have to find out what the best way to go if we have the ability is to make this go to 0, and that will give us the best option. We usually don't have that as an option. Okay. Okay, so let's look at a circuit with a we'll look at the power, the load power, and let's find what it's equal to. Power equals, in this case, V squared over R, L, and we find what it is. V squared is 0.5 volts divided by 50, or 5 milliwatts. Okay. Here, we then look at it from the point of view of matching the RL to various values. If we set it to the 1 ohm, we find the current, and we find the power. So we set it to 1 ohm, we set it to 2 ohms, we set it to 0.5 ohm, and we look at each of those cases, and then we ask what is the power. So at 1 ohm, we get 1 watt. Moving the wiper to 2 ohms, we get 2/3 of our resistance. Okay, so we get 2/3 of 2, or 1.33 volts. But look what happens to our current. Our current goes down, and it goes down to the rate of 0.667. So 1.33 times 0.667 gives us 0.887, which is less than 1. So if we go to 2 ohms, we're dropping a little bit, but not a lot, but we're certainly less than we were at the maximum. Okay. Now if we go to 0.5 ohms, 0.5 times 1.5 times 2 is 0.667 volts. So we've dropped our volts. Now our resistance, our current is 1.33. So now we will multiply 0.667 times 1.33, and again we drop to 0.887, which is less than the 1. So either way we go, we drop a little bit on the plus side or a little bit on the minus side, our power goes down. So again, this isn't a proof, but it gives us some comfort that we found the method for finding the maximum power output from a given theoretical or a given Thevenin equivalent circuit. Okay, so that gives us a look at the first part of this chapter, and the next assignment we'll go through the problems. Take care and have a good day. Okay, we're working now with the problems at the end of chapter 4, and we're going to go through them, and starting with problem number 4.1 on page 13 of chapter 4. So this problem says find the voltage of the 10K resistor for 417A. And we're going to, so we have on 417A, we have a 2 milliamp current source. So that means we're guaranteeing 2 milliamps. It's going to flow through a resistor of 10K. So it wants to know the voltage across the 10K. Well, it's V equals IR. V is equal to 2 milliamps times 10K, or that would be 20 volts. So our answer, voltage across the 10K, is 20 volts, plus to minus, plus 20 minus. Number 2, 4.2. In figure 417b, the resistor is a 10K pot. When the wiper is at the top, what is the voltage? When the wiper is at the bottom, when the wiper is in the middle. So basically now we have a 3 milliamp source, and we have a pot, and we have a wiper that we can pick off a resistance at. So we have a 10K pot. So if it's all the way to the bottom, it forces it to go all the way through the 10K. If it's all the way at the top, there's no resistance. So if we have at the top, there's no resistance, R equals 0, and if R equals 0, and we have 3 milliamps, V is equal to 0. If R is equal to 5K when it's at the bottom, R is equal to 10K. So in that case, we have 3 milliamps times 10K, or V equals 30 volts. If we're in the middle, R is equal to 5K. So with 5K times 3 milliamps, we have V is equal to 15 volts. Okay, so number 3, 4.3. If you were to have in your hand a number of resistors in the range of 10 ohms to 1 megohm, what would be the max value across the AB terminals of figure 417C? If only one resistor was attached, what would be the minimum value across the AB terminals, the max current and min current? Okay. So if you have your hand a number of resistors from 10 ohms to 1 megohm, okay, what would be the maximum value across the AB terminals for each of these situations? What would be the maximum value across the AB terminals? Well, if you want to have a big output, you have to have a big resistance. Okay, so we have 2,000 volts. We have 100 meg up here. So we're going to basically say, if I attach a resistor out here, how do I make the voltage across here the biggest possible? So if you were to put like a 10 ohm across here, let's do that. The current is 100 meg, or excuse me, is 2,000 volts divided by 100 meg, 100 and then 3 more zeros for the thousands, and then 010, and that equals, the current is equal to, I is equal to 1.99 times 10 to the minus fifth, or 19.9 microamps. And then you multiply that times 10, and you get 199 microvolts. or 0.199 millivolts. Okay. Now we start putting a bigger number in there, 1 meg. If we put 1 meg in there, we're actually going to get a little bit less current, but the voltage is going to go up. So let's put in 1 meg ohm. So let's do that. So the current is going to go down just a little bit, but the voltage is going to go up. So let's look at it that way. If you have 1 meg ohm and you have 101 meg, so that would be 2,000 divided by 101,000,000, and that is that. So that is the I is equal to 19.8 microamps. If you multiply that times 1 meg, or 100,000, that gives us 19.8 volts. So our voltage, 19.8 volts. So small ohms, small volts, even though that's the biggest current. Big ohms, biggest volts, and a little bit smaller current, but not by much. What does that mean? It means this is a constant current source for the most part. We basically limited it to 19.9, 19.8 microamps, but it's still basically giving us more voltage when we have a bigger resistor across it. Okay, so that's giving us an example of a okay. So we found the min and the max, and that's all we need to know. Okay, so that's number 3. 4.4. For figure 418A, find the Thevenin equivalent circuit. So let's go down and look at 418A. So for 418A, we have 2 milliamp current source, and we have a resistor in parallel, which is 20k ohms. So what does this look like? This looks like our Norton. So this is Norton. So how to convert Norton is to basically do the voltage, which is V times I, or 40 volts. 2 milliamps times 20k is 40 volts, and move the resistor over to the 20k spot, and you're all set. So basically, just move this over, multiply V equals I times R, and you're all done. So that's what you have to do for 4.4. So the next one, 4.5, is the same thing with B, with the figure B. Okay. So with B, we don't have quite the same thing, but we're close. Okay. And I'm going to show you a trick here that allows us to pretty much do this very, very easily. So we got 3 milliamps, we've got 6k, right? We have 3k up here. Well, this part right here is the Norton. So if I do the Thevenin equivalent of it, what do I have? I've got 3 times 6, or 18 volts. And I have up here, for my rest of it, I have my 6k. So I basically move my 6k up here. Now I add my 3k in up here, and I've got my rest of my circuit. So what do I have? Well, this combined is my R Thevenin. So I now can look at it and say I've got 18 volts, and I've got 9k for R Thevenin, and I'm done. So if you look at it, you cut this, and then you say convert this part to its Thevenin equivalent. 3 times 6 is 18. Move the resistor up, then you just combine the two, and you're done. So that's all you have to do for that one. For 4-6 or 4.6, it says find the Thevenin equivalent of 418C. So this one is the same, except for now I've got another resistor in there, and really that other resistor doesn't really matter, but we're going to have to do a little bit different for this one. So we're not going to be able to play the same trick for this one, because we've got this resistor up here, which really it's just an outlier. We don't really need to worry about it, but let's worry about it and see where that gets us. 6K, and we've got 3K over here. Now we really do have to concentrate on where does the current go and what is the voltage across it. So if we look at this circuit, we say, what is VAB? Well, it's the voltage across this 6K. Well, all this 2 milliamps has to go this way because it can't go this way. So VAB is equal to 6K times 2 milliamps, or 12 volts. Now for R Thevenin, we start at this point, we come back, R Thevenin, we have 3K, and then we can go this way, but we can't go this way because there is no way we can get through that way, so that the road is blocked. So we have the 3K in series with the 6K, and that's the only way we can go. So we can go this way, but we can't go this way. So the resistance, R Thevenin, is equal to 9K. So we can redraw the circuit, 12 volts and 9K, and we're done. We're done. So that's 6. 7. Find the Thevenin equivalent left of the CD terminals of figure 418D. Then find the equivalent circuit left of AB. Okay, so first of all, so for 4.7, we look at find the Thevenin equivalent circuit left of the CD terminals. Okay, so the first thing we do is we look at the 9 milliamps going through the resistor. Okay, so that's the first thing, and we can do that real quick because we can convert this immediately to Thevenin equivalent, and that would be 9 volts and 1K. Now we attach, we've got a 2K up here. We have 6 volts, or 6K. We've got our AB terminals. Okay, so this combines into a 3K, and now we can find VAB, which is equal to what? 6 over 6 plus 3 times 9, or 6. What is R Thevenin? What's 6K in parallel with 3K, or 2K? So our final answer is 6 volts and 2K. And that's our Thevenin equivalent circuit for 4-7. Okay, so 4.8, we're looking at E, which is a little different. This is a superposition problem. And in this one, we can concentrate on what would be the voltage of the 10 volts and the 1 meg. The 1 meg. And the current supply. Now, we do not know what that voltage across that current supply is. We do not know. So it says find when ICBO is 1 microamp. Okay. So the rules say this: do it with just the voltage supply, and the 1 meg, and the current supply open. So the voltage across the output would be 10 volts. There's no current flowing through that 1 meg, so it's 10 volts. Any questions about that? So just using voltage supply, not the current supply, you get that. Now let's do it with the other way around. Let's do it with the current supply. And one meg, and then the short, the short across the output. Now we want to know the value across this, which would be the value across here. So what would be 1 microamp times 1 milli? 1 times 10 to the minus 6 times 1 times 10 to the 6th is 1. So the voltage across here is 1 volt. So you add the two together. 10 plus 1 is 11 volts. So the Thevenin equivalent circuit is 11 volts. And R Thevenin is equal to 1 meg ohm. Okay. 9. For 19A, find the Norton equivalent circuit. So this is going to the Norton side. Okay. So if you find the Thevenin equivalent, you can find the Norton equivalent. That's the way I always do these, plus or minus 6K, 3K, 1K. All right. So how would be the Thevenin equivalent circuit? Well, it would be voltage would be 3 over 3 plus 6 times 9, or 3 volts. R Thevenin is 2K in, well, it's 6 parallel with 3, or 2K plus 1K, or 3K. So we have 3 volts and 3K. So what would be our current? I shorted load is 1 milliamp. So our Norton equivalent is 1 milliamp, I shorted load, and our R Thevenin is 3K. So that is Norton equivalent circuit. Okay, that's 9. 10, find the Norton equivalent circuit left of the AB terminals. So 4.10. So we have 27 volts, and we have 3K, we have 6K. So 6 over 6 plus 3 is 2/3, and it's 18 volts. And R Thevenin, V Thevenin is equal to this. R Thevenin is equal to 6K in parallel with 3K, or 2K. Now, what would be I shorted load? I shorted load is equal to what? (18 volts) divided by 2K, or 9 milliamps. So we can redraw our circuit, 9 milliamps. (2K), there's our Norton. Okay, that's number 10. (4.11). Find the Norton equivalent circuit left of the AB terminals for 419C. 419C. Okay, so 419C is 9 volts. (6K), 3K, and 1K. So what would it be? So we have 3 over 3 plus 6 is 3 volts. So the Thevenin equivalent is 3, and then resistance is 1, and 3 parallel with 6, or 2, so it's going to be 3K. So I shorted load is equal to 3 volts divided by 3K, or 1 milliamp. So now I can redraw this. 1 milliamp in parallel with 3K. That's my Norton equivalent. Okay. Then find the Thevenin equivalent circuit. We already did find the Thevenin equivalent circuit. There's the Thevenin equivalent. And then the Norton equivalent is what we just did. Okay, find the Norton equivalent circuit left of the AB of 419D. So this would be number 4.12. And this one I'm going to do it's got 12 milliamps. It's got 3K. And then we've got a 6K up here. So I'm going to turn this into a Thevenin, and it's 3 times 12, or 36 volts. And you put your 3K up here, and you've got 6K over here. We just add those two together, right? That's 9K. So our Thevenin equivalent is 36 volts and 9K. What would be I shorted load? Well, it's 36 divided by 9, or 4 milliamps. So that's our Norton equivalent, 4 milliamps, and 9K. So that's our Norton. And that's it. Okay, 12. Boat battery dissipates 24,000 joules in 10 seconds. Find the kilowatts. Okay, so that's joules per second is 24,000 in so many seconds. In 10 seconds is 2,400 watts, or 2.4 kilowatts. 13. Battery outputs 9 volts, and the current is 10 milliamps. What is the power dissipated? Well, watts, or power, is V times I, or 9 times 0.01. So that's 0.09 watts. $14. Okay, so we have now find the power dissipated in the 5K battery, or the 5K resistor of figure 420A. This is 14. And the 15K resistor. So basically, if we know I is equal to 20 volts over 20K, or 1 milliamp. So I now know my I, and I can say which would be the better one. Is it V times I, or is it I squared R, or is it V squared over R? Well, I know I and I know R, so I can just say this one is the best one. Okay, so let's use that. 1 milliamp, the quantity squared, times 5K. So that is 0.01 quantity squared times 5,000 equals 0.5 watts. And the 15K resistor, that would be for the 5K. For the 15K, it's 1 milliamp quantity squared times 15K. What does that be equal? I bet it's 1.5, but let's just do it. It's 0.001 quantity squared times 15 with 3 zeros. That's 0.015 watts. Let me do the 1 milliamp again. Let's see. Okay, so 0.001 quantity squared times 5,000. and that's 5 times 10 to the third, so that's 0.005. Okay, so that's 0.005 watts and 0.015 watts. That's the answers for 14. Okay, what would be the total? In the total R, it would be these two added together, so 0.005 and 0.015 would be 0.02 watts. Now we look at number 15. We say, what would be the power dissipated in each of these resistors? So in number 15, this would be easy with what? 24 volts, and we've got a 3K. We have a 4K and a 6K. So this would be easiest with V squared over R, wouldn't it? So so we have V and we have V squared. So 24 squared divided by 3,000 is equal to 0.192 watts. 24 squared divided by 4,000 is equal to 0.144 watts. 24 squared divided by 6,000 is equal to 0.096 watts. So you have these all together, and what do you get? I get 0.432 watts. Okay. Now we go to C. Here we have to find the voltage across each resistor. So let's just 12 volts, and I have 1K up here, and I have 3 and 6, so I'm going to say it's parallel would be a 2K here. So I can split this voltage, and I can see that the voltage across the 1K is 1/3, or 4 volts, and I can see that the voltage across the 2K, or the 3K and the 6K, is 8 volts. So I can see that the voltage now in the 1K is what? V squared over R, which should be 4 squared divided by 1K, and I can see the voltage in the 3K is 8 squared over 3K, and in the 4K it's 8 squared over 4K. So now let's do the 64 divided by 3,000 is equal to 0.0213. The 8 squared divided by 4,000 is equal to 0.016. And the 4 squared, or 16, divided by 1,000 is equal to 0.016. These are in watts. So 0.016 plus 0.016 plus 0.023. Okay, so it's 0.016 plus 0.016 equals plus 0.0213 equals 0.0533 watts. Number 17. With the power supply of figure 421A, assume R Thevenin is equal to 0. Find the power dissipated if the voltage is set to 10 volts, 30 volts. So this is number 17. So if the R Thevenin is 0, find the power dissipated if voltage is set to 10 volts. So it's V squared over R. V squared over R is equal to 10 squared divided by 100, which is what? 100 over 100 is equal to 1 watt. If you have 30 volts, it's 30 squared over 100, or 9 watts. So that's 17. Okay, this is talking about now a fuse when there's a short between the A and the B. Okay. So if we have a 1K and 15 volts and we have a short between A and B, what would be the fuse value? It's a little bit greater than the amps. So it would be 15 volts divided by 1K, or so this is 18. Fuse is going to be greater than I. So the I short circuit would be shorter load. So it's equal to a little more than 15 divided by 1K, or 15 milliamps. So it has to be a little bit bigger than 15 milliamps. If there's a 2 ohm resistor between A and B, well, not much more than 15 milliamps, but you say 1002, okay, and that's it. There's a 75 ohm resistor between A and B. Well, that one gets a little bit more, so it'd be 15 divided by 1075, and that's equal to what? It's 0.133, so it's 13.95 milliamps. So the fuse size goes from a 15 milliamp down to a 13.95 milliamp for those. Okay. Now for 421C, it says find the maximum load power. Okay, so this would be for 19. 419. Okay. For figure 421C, find the maximum load power. So here we have 12 volts, and we have 9K, we have 18K. All right, so we've Thevenized this, and we get 2/3 of 12, or 8. 18 over 18 plus 9 is 8. It's 2/3 of that. 18 in parallel with 9 is what? 18 times 9 divided by 27 is what? 6. So we drop to 6K. Okay, so find the maximum load power. If to find the maximum load power, you have to set this to 6K. So now what would be our voltage? What would be our current through this circuit? Well, it's 8 divided by 12. 8 divided by 12 is what? 12K. 0.66 milliamps. So I squared R is 2. Okay, so I squared, so it's 0.66 times 10 to the minus third squared times 6K. So it's, we got to get our units right. 0.66 squared times 6,000 equals, oops, 0.00066 squared times 6,000. So it's 2.61 times 10 to the minus third, or milliwatts. 2.61 milliwatts. Okay. Number 20, is an antenna, and that would be, for an antenna, B Thevenin is equal to 100 microvolts. And R Thevenin is equal to 50 ohms. Find the maximum load power. So here we have 100 microvolts. We have an R Thevenin of 50. We have an output of 50. So we now find I. It's 100 microvolts divided by 100 ohms, or 1 microvolt. Okay, so I squared R is 1 times 10 to the minus 6th quantity squared times 50. Okay, so it's 0.000001 times 50, or 50 micro watts. That's 420. 421, adjust 421D, adjust R Thevenin to get the maximum power load across that circuit. Okay, find the maximum power at this point. So for 421, the best thing to do is to find, to get the most out, you put the 10 volts and you put the R Thevenin is equal to 10K. And the R over here is 10K. So now let's find I. I is equal to 10 divided by 20K. And that would be what? 0.5 milliamps. 0.5 milliamps squared times R. 0.5 times 10 to the minus third quantity squared times 10 times 10 to the third. So it's 0.5. Okay, it's 0.0005. Okay, that's 0.5 milliamps squared times 10. 1, 2, 3. So we got that. That's 2.5 milliwatts. That's 21. Okay. So in D, now it says, now adjust R Thevenin to 10K. Okay, so I think I made a mistake there to find, so I just solved the question for 22 when I just did that. So now let's go back and let's do 21 again because I made a mistake. 21, the adjust R Thevenin to get the maximum power across the 10K. So to get the maximum power across the 10K output, you make R Thevenin equal to 0. So I just solved for 422. This is 422. Okay, this is the answer to 422. The answer to 421 is, sorry about that, 421, the answer to that one is if you make R Thevenin 0. So if you make R Thevenin 0, you get your maximum power out. Okay, so 10K and 10 volts. I is equal to 1 milliamp. Okay, so now you say I squared R, 1 times 10 to the minus third squared times 10 times 10 to the third is equal to what? Okay, so this is 10 to the minus sixth times 10 times 10 to the third. So I get 10 times 10 to the minus 3, which would be 10 milliwatts, not amps, but milliwatts. So that gives me my answer for 421, okay? So that's the answer to 421. And we answered 422. Now let's go to 423. So we have a black box as a V Thevenin of 10 and an R Thevenin of 600 ohms. All right. So 423. V Thevenin is equal to 10. And R Thevenin is equal to 600. Find the maximum load power. Okay, so in this case, we have a circuit that's already built for us. So we've got a 10 over here, we've got a 600 up here. Get the maximum power out, you put a 600 across the output. And then you calculate the power. Calculate that power. So basically it's 10 divided by 1200. Or 8.33 milliamps. Okay, so now you say I squared R, unity squared, times 600. Or power is equal to 0.0416 watts, or 41.6 milliwatts. Okay, so the best way to do it is I squared R, and that gets you the best answer. Okay, 24. So for 24, we're going to figure a bunch of different circuits. I want to see where the best power out is. So you're just going to do the same problem a number of times. So basically you're going to work 424 a number of times. In each case you're going to say, you're going to basically prove the matched power load, the max power load, and where does it occur. So I've got 10 volts, and I've got 50 ohms up here, and then I'm going to put various resistors across here. I'm going to put 0, I'm going to put 25, I'm going to put 50, and I'm going to put 100, and I'm going to put an open circuit. So basically, in each of these cases, when I hang a resistor up here of some value, I have to find the I or the V, and then do the I squared R or the V squared over R. So let's do R equals 0. R equals 0, the I is equal to what? 10 divided by 50, or what? 0.2. 0.2 amps. Okay, so 0.2 squared times 0 is equal to 0. Okay, then you put in 25. R is 25. Okay, I is equal to 10 divided by 75. Okay, 10 divided by 75 equals 0.133. Hit the square button, and then times what? 25. That gives me my output. So the output here, power, is equal to what? 0.444 watts. R equal 50. I equal 10 divided by 100, or 0.1. P is equal to I squared, now square that, times 50, or 0.5. So power is equal to 0.5. Now I go to R equals 100. I equals 10 divided by 150. Okay, 10 divided by 150, 0.066. Hit the square key, then you multiply by 150. Answer is 0.666. Whoops, made a mistake. Okay, so R is 100, I is 10 divided by 150 equals 0.066. Hit the square key. Okay, that's I squared times R. It's 0.666. Do it again. 10 divided by 150. 0.066 squared times 150. Hmm. 0.666, which is bigger than a 0.5. Let's go to 10 divided by 100. Hmm. Okay, I got this wrong. I was multiplying by 150, and it should be point by the 100 instead of 150. So that's where my mistake was. So it does go down. Sorry about that. So it's multiplied by I squared times 100 is 0.444. So it's I squared times 100, not 150. If you did 150, it would be greater, but it's not. It's 0.44. So you see the maximum is where this is equal to this. In other words, this is equal to that. And that proves, again, the maximum power law. So I'm sorry I made a mistake there, but that's okay. We all can make mistakes. Take care. Have a good day. Bye.